Hello guys, it's Fabrizio Gianni7 here. This is an amazing place to create videos about what I don't understand in Web3. So this summer I decided to create a video about DA, aka data availability. I did this video because in first place I didn't understand what DA is. I want to understand why we have DA. So I did some research. I tried to gather these researches and make a video, an intro explainer to DA. So I will explain what, how and why. The goal of the video is letting people understand and have a broad idea of what DA is. Many things are simplified for letting people understand what I'm talking about. Hopefully you will enjoy this, and please comment if you have any doubt. Thank you guys, enjoy the video.
So what the hell is data availability, or DA, in public blockchains? DA guarantees that all the informations needed to validate the transactions are easily accessible. In fact, in order for the blockchain to work, each blockchain participant should be able at any moment to access transactions data to validate them. Okay, stop. To understand what is DA in blockchains and why it exists, we need to know what is a blockchain, how is it composed, and how it works. A blockchain is essentially composed by nodes that create blocks which contain informations about the transactions performed on the blockchain. Now, what is a node and how the heck blocks are created? A blockchain node is a computer connected to a network of other nodes, which role is to verify transactions that users send on the blockchain. Nodes create new blocks to add to the blockchain. To do so, they perform a series of actions. The nodes get and execute transactions sent by users. In the execution phase, the nodes need to get the transaction history and check the validity of each transaction. Next, there is a phase where all the nodes reach an agreement on the transaction validity and order. At the end, there is a stage called settlement, where the new block is created and finalized on the blockchain. Let's try to split these phases in different functionalities: execution, consensus, settlement, and data availability. We saw the execution when the node validate and execute the transactions. In this functionality, the execution layer of a blockchain need to access the transaction history. That means that the data about the transactions need to be reachable. And guess what? In order to get this data, the execution layer will communicate with the data availability layer. I'll talk about that in a few moments. Consensus is the way the different participants of the blockchain agree on the validity of a transaction and their order. Settlement is basically the way the block actually lands on chain. It refers to the process where transactions are finalized and recorded permanently on the blockchain. And finally, we talk about data availability. DA guarantees that all the informations needed to validate transactions are easily accessible. Each node needs to access the transaction data in order to be able to validate them. In L1 blockchains, nodes typically are able to perform all these functions in the same environment. And that's why blockchains like Ethereum are called monolithic. There is a big catch with monolithic blockchains. They are not scalable. This model is not scalable because it requires more resources to run a full node, to validate the blockchain and create new blocks. The full node requires a lot of resources, like storage or computational power, in order to get the blockchain transactions and verify the state. So that's the scenario. The user base increases, users create more transactions, blockchain size increases, and using the blockchain becomes more expensive. To scale the blockchain, there are higher hardware requirements. Having a node becomes expensive, and blockchain is now less decentralized, because only rich people can run nodes and users will give up on using it. The solution to this is something called modular blockchain. A modular blockchain is a chain that focuses on one or two between execution, settlement, consensus, or DA. For instance, you could have a modular stack composed by an execution and a settlement rollup taking care of executing and validating transactions on top of a DA layer. An example of modular blockchain is an execution layer, like an L2 rollup, posting some kind of execution proof to an L1, which is then handling all the other blockchain functions. So what is DA? And what's the difference between DA and DA layer? Data availability is a core function of the blockchain needed to make transactions available for who want to validate the blockchain state. Let's start from this concept. In general, to validate block data, a DA layer needs to prove that data of a given block is available. A data availability layer is a modular blockchain that performs data availability. There are many data availability layers like Avail, Celestia, or EigenDA, to mention just a few of them. For now, to explain how DA works, I'll take as an example Celestia, and I'll try to explain its techniques. Celestia is a modular blockchain composed by full and light nodes. Full nodes are resource-expensive nodes that hold all the transactions. Light nodes are nodes which require less resources that use advanced techniques to validate data contained in full nodes. Light nodes are fundamental for Celestia because they are scalable and are able to use advanced techniques to provide data availability. Some of these techniques that Celestia use are called data availability sampling, or DAS, and namespace Merkle trees, or NMTs. Those are advanced techniques that allow data availability layers participants to verify blocks without necessarily having to run a full node. Let's look briefly into data availability sampling. Celestia splits block data in small samples. Every light node validates each sample against a Celestia full node. If many light nodes verify that these samples are available in full nodes, it means that it's very likely that the full block's data is available. DAS allows Celestia to scale the DA layer. Since light nodes need to sample a small portion of data, this requires less space and are more affordable. The more light nodes are in the layer, the more data samples can be validated. Now let's look into namespace Merkle trees. Celestia partitions the block data into multiple namespaces. For instance, it can divide block data based on the rollup, so every rollup will have its own namespace. This way, every application needs to download only its own data and ignore data of other applications. To validate block data, the DA layer needs to prove that just data for a given namespace is available. These samples are then inserted into a Merkle tree. Namespace Merkle trees are data structures needed to order the data by namespace. The root of the tree contains the block header, which is generated with an hash function, which includes all the namespaces. Then each leaf got a range of the namespaces, and so on until getting to the data sample of each namespace. For instance, the header hash includes namespace 1, 2, and 3. The left leaf contains namespace 1 and 2, the right leaf contains namespace 2 and 3, and so on until getting to the data. As you see, every light node will contain a data sample referring to a namespace. And to prove that the data is there, nodes should provide a Merkle proof. And I'll put some link in the description with a good explanation of what is a Merkle proof. So during this video, we understood that DA in blockchain refers to the practice of making transaction data easily accessible and verifiable. We discovered that there are DA layers like Celestia, Avail, or EigenDA that allow anyone to rely on them for data availability. What can developers use these layers for? Well, the most common use cases are actually custom L3 blockchains and scalable decentralized app chains. Let's make some example. Arbitrum Orbit allows you to spin up your custom blockchain. Devs can choose, for instance, the language to write smart contracts, choose a custom gas token, and the DA layer they like. This way, devs could, for instance, build a public blockchain where you can write smart contract in C++, use any ERC20 as a native gas token, and use any DA layer they want for data availability. Another use case example are Cartesi Rollups. To be very quick, Cartesi allow devs to create applications on a dedicated rollup with a specific CPU. You can basically create app chains with dedicated resources. This way, other dApps won't use the app resources, and the app will be extremely efficient. A dev could build an app chain to run, for instance, a decentralized on-chain version of Midjourney, using a dedicated CPU to make AI inference off-chain and posting a sort of computation proof on a DA layer. Devs could build any type of application this way, actually. So we discovered what is data availability, but what are the advantages? Basically, using a modular approach to blockchain development reduce transaction costs and make applications faster comparing to applications built on monolithic blockchains. Also, making the blockchain scalable allow new use cases to run on the blockchain, like artificial intelligence. And that's a wrap, guys. I hope you liked the video, and if you arrived so far, please comment "no pineapple on pizza," and you will have some surprise later on. See you soon, people, and take care.